discuss this topic of phase transitions today. Uh, so I wanted to mention about this book. When if you ever take a advanced statistical mechanics course after you finish your MSc and go to PhD, then this kind of book will be what you will follow. So this is book by Giuseppe Masardo, Statistical Field Theory. It's an introduction to exactly solvable models in statistical mechanics. So I will use this book, this first chapter of this book, discuss phase transitions. So essentially, the phase transitions are um, classified into two types, and namely, first order and second order phase transitions are continuous or discontinuous phase transitions. And before that, let's try to understand phase transitions. Phase transition basically takes place because there is two processes. Okay, so competing, these are like competing processes. This one of it will try to minimize the energy, and second process will try to maximize the entropy. So I will try to discuss these phase transitions, where I will run through an example of some example system. Okay. So that will be kind of a magnetic system. So, so we choose magnetic system as an example. To the discussion. Even though the conclusions that we are drawing from this discussion are generally valid for other phase transitions, just for concreteness sake, we will try to choose magnetic system as an example. So, what we have in this magnetic system is basically a collection of magnetic dipoles. And since we are studying a solid on a lattice, so that is what we are interested in, solid state. Thus, the is material is made up of a solid, and hence this collection of magnetic dipoles. This magnetic dipole moment can arise from spin, or it can arise from orbital angular momentum, or it can arise from both the total angular momentum. And when we are taking a particular system, then we have to understand what is the mechanism of the emergence of this dipole. But that question we will not worry at this moment. Let's say that dipoles are given, and we will study, given this set of magnetic dipoles on a lattice, how do we understand the ground state and the behavior and so on. So if you look at a typical Hamiltonian of the system, which is what determines the interaction. Typical Hamiltonian will be something like this. The Hamiltonian of the system is minus j over 2 and sum over ij and si dot sj. I'm writing like this doesn't mean it is spin operator, it's just an angular momentum operator. And this notation for sum implies sum is only over nearest neighbors. Nearest. That means if you think that you have a lattice like this, 1, 2, 3, 4. So let me just draw a two-dimensional square lattice. So if you have a lattice like this is what I have drawn is a 4 by 4 lattice. And suppose if I have some dipole moment here, and this dipole moment will interact with its neighbors. For example, this dipole moment may interact with this, it may interact with this, it may interact with this, interact with this, but it will not interact with the next nearest neighbors. That is the meaning of saying in this sum, the interaction is only over the nearest neighbor. This is obviously an approximation, but it is generally believed that the interactions are short range. They don't interactions at least die down when you go far away from the point where you are interested in calculating the interaction. Now this j is at this point is some constant, and this is you will learn when you actually study some magnetism. You will see that this comes basically from quantum mechanical exchange uh, exchange symmetry of the wave function. But let's not go into details. But it is also a consequence of the Coulomb force between the electrons, and so we will leave it at this point. So J is J greater than 0 is constant, and this is uh, what determines, in some sense, the strength of the interaction. Strength of interaction. Now notice the nature of this Hamiltonian is such that if all the spins are in the same direction, okay, so you can draw this conclusion that if all uh, dipoles all dipoles are aligned, then your si dot sj for all ij will be what is called they are one. Suppose let's say this has a magnitude 1, then they are just 1. So you get if all dipoles are aligned, we get what is called minimum energy. Minimum energy. And the system would always try to minimize energy. And if this is the only process, if the energy minimization is the only process, we must always get a configuration where all the spins will be aligned in the same direction. Okay? And usually we call such magnetic system as ferromagnetic system. And what happens if all the spins are aligned in the same direction? There will be a very high magnetic field around such a material, and all materials must be kind of a magnets. But we don't see this kind of a thing happening. So it is not that. There is another competing interaction, that is system would also tries to maximize the entropy, and that will so there is a competition between these two processes, and that is what leads to uh, and this maximization of entropy is governed by thermal energy, or essentially the temperature. What is the temperature? And hence, at some temperature, there is a phase that is dominant by the process of maximization of entropy, and at some processes there will be a phase that is dominant by the process that minimizes the energy. And these two competing processes is what leads to a kind of a phase transition. Okay. So if we have only one of this process, suppose if maximization of entropy is the only thing that is possible, or that is at operation, then you always have a disordered phase. If minimization of energy is the only process that is contributing, then you'll always have an ordered phase. Variety of phases, and here we have uh, what is called a phase transition, that is paramagnetic paramagnetic to ferromagnetic phase transition. Ferromagnetic, and usually this is paramagnetic phase is in general you can say that disordered disordered to ordered phase, disordered to ordered phase. And as the temperature in the disordered phase is higher, okay, so temperature is lowered, then the thermal energy decreases, and as a result the interaction can dominate and you get an ordered phase. So this is high temperature, and this is low temperature, and there will be some particular temperature at which this phase transition happens. So this is I'm just showing you here in this picture. You can see that uh, there is some kind of a temperature Tc. It is called Curie temperature. Curie temperature. And above Curie temperature, there are domains which, there within the domain there is some kind of an order, but uh, domains are not ordered like this. But below Curie temperature, there is a perfect order. So you can say that this kind of a phase transition happens at EC, which is called the Curie temperature. So this is an example of a phase transition. As you can see, the macroscopic behavior of the system will be very different on either side of this phase transition. For example, here, if it is in a disordered phase, then there is no magnetic field around that. It doesn't act like a magnet, but it can be magnetized. You apply magnetic field, maybe you can magnetize that one. But below TC, it is a ferromagnet. That means it is all the spin, all the dipoles are oriented in one particular direction. So this is an example of a phase transition. But generally, the phase transitions, as I told you, that uh, there is a classification. This There are two types of phase transitions classification. So first is called first order or discontinuous continuous phase transition. So in this case, what happens is that your first derivative of the free energy will always show a discontinuity. For example, you take if you take this kind of a phase transition, let's say this is your pressure and temperature, and this is what we call as EVT system. That means any gas liquid solid kind of a phase transition. So you see that it will have a triple point, and then there will be a liquid gas coexistence curve which will terminate at a critical point, and then there is a solid liquid coexistence curve which does not terminate. This is liquid gas. Now, in this kind of a this is a in this phase transition, you can see that there can be solid to gas transition, which is called sublimation, and solid to liquid, which is called melting. Liquid to solid is called freezing. So this is basically a coexistence curve. So you can have a phase transition from here to here, or from here to here. A phase transition from solid to liquid, or liquid to solid. A phase transition from solid to liquid to gas, and gas to liquid. So all these phase transitions that I have drawn arrows here, they are all first order phase transitions. So in first order phase transition, you have what is called a latent heat is involved. Latent heat. That means when there is phase trans, so when the system reaches that temperature, then the heat is absorbed by the system, but there is no rise in temperature. So it will, in the coexistence curve, the temperature will not rise, and unless the phase change is complete. So that is what is very what is called a differentiating aspect of first order phase transitions. Latent heat is involved, and further you can see that uh, you can see that a part of the system is converted into the other phase. Like for example, when you take freezing of water into ice, so you can see some part of the water will be converted into ice, some other part is yet to be converted. So as you give more and more heat, then the whole water is converted into ice. So this kind of latent heat is very important. Of course, there is no phase transition between liquid and gas above the critical point. So this point is very important. It is called critical point, and gas to liquid, liquid to gas phase transition at critical point is not first order phase transition. That is very important to understand. The second one is second order or continuous phase transition. Order or continuous. Here there is no latent heat is involved. First order derivatives are not continuous, but this has its own interesting features which we will discuss mainly in today's lecture. So in the second order phase transitions, so one of the examples is liquid to gas, liquid gas transition at a critical point. At critical point. This is one example. Of course, the second example is paramagnetic to ferromagnetic transition. Paramagnetic to ferromagnetic transition is second order phase transition. Third example is um, normal metal to superconductor. So this is another example, and then you have normal liquid, normal liquid to superfluid. Superfluid in helium, especially. In helium, you observe that normal liquid to superfluid transition. So these are some examples of second order phase transition.
Sir?
Now, in second order
Sir?
phase transition, yes,
So what about coil to globule transition polymers?
yeah. So coil globule transition is also second order transition. So that also is coil to globule. Uh, Polymers. Uh, like for example, okay, their spins direct. Ten lattice spacings. The spins are oriented in the same way, are over, let's say,
Sir?
100 lattice.
So the presentation is not visible, sir.
What?
The
The screen share
presentation.
presentation.
Presentation is not seen.
Yes, sir.
Yes, sir.
Now,
Yes, sir.
do you see it now?
Yes, sir. Yes, sir.
Okay. Okay. So these are different examples. So now we ask a question that how these correlations are correlations are correlations are important. So normally what happens is that we get some information about these correlations in some scattering experiments. Okay, so we go to some scattering experiments. Like for example, if you take light scattering experiment. Okay, so if you look at some scattering experiments give us a wealth of information about what happens at phase transitions. For example, when you take the system of liquid gas to liquid phase transition at critical point, that is, let us look at this example: gas to liquid phase transition at critical point. Then you will see that there is nothing like there is a particular solid phase that is nucleated and it is growing. Then you will see that here you have a small clusters of liquid and then gas. Then you have bigger ones like this. Then you have something like what is called droplets of all sizes. All sizes are present. So when you are sending in light, okay, then what happens is that there will be some kind of a reflection of light of all wavelengths, and then you get something like you get a milky white scattering that you see, and this is what we call as critical opalescence. Critical opalescence. Okay. So similarly, a similar information you can obtain from the magnetic system by sending in a neutron beam, because neutron beam magnetic moment, and from scattered from a magnetic system, we can understand the appearance of scale. I mean, a larger scale. So what happens at second order phase transition is that the correlations, okay, they are. Uh, it turns out that the correlations at the transition point, at the critical point, they are long range. That means there will be correlations in the entire system. That means if you have a spin here and you have probably another spin at the edge of the system, but that will be correlated to this. So this appearance of long range correlations is very central to uh, to what is called a second order phase transition. Okay, so I was just trying to show you what this correlation is here. So you can see, let's say this is this dotted line shows that all the spins are aligned in the same direction, and outside this region you have, of course, spins. I mean the magnetic moments in different directions. So this particular region, you can say, is there is a perfect correlation, and we get this. We get this 1 minute. You can see the screen.
Yes, sir.
So you can see that this particular correlation length. So this xi is called the correlation length. So the important aspect is that we have correlations, and we can define what is called correlation length. Now, the correlation length is defined by actually defining a correlation function. So this G2 of I comma j is defined as Si dot Sj if they are, but you can also talk about an average behavior. That means this you can define this S0 as if there are n number of spins, you can talk about 1 over n, I is equal to 1 to n, and Si. So you can say this is the average value of the spin. Now I want to know how much is the fluctuation, so I can remove that average value from each one of this quantity, and then look at the correlation of that. Okay, so that is what is given by this. Now I have to say that this one will go like this. That means there are correlations only at a distance smaller than this xi, and from xi onwards there is no correlation. Of course, the a is your lattice parameter, so this is larger than the lattice parameter. A
Sir,
is the lattice. Yeah.
sir, sir, is correlation length is related to opinion formation theory, sir?
What related to what?
opinion formation theory, like one person is influences his nearest neighbor.
Yeah, yeah, yeah.
So, so
Opinion formation theory has at some level you can model it like that, but it is not so inanimate like this. No, opinion formation is always involves some psychological aspects.
yes, sir. But
Yeah,
it's like ferromagnetism. Like the nearest neighbor
exactly,
is influenced by a person, and he also
exactly.
influences.
So
Okay.
that part of it is common. I mean, same as what we are discussing here.
Okay, sir. Okay, sir. Thank you.
Yeah. So what I'm trying to show here is that uh, how do we define this correlation length? Okay, so the correlation length is defined in this fashion. Now you can see that. Okay, so before that, we have to define something which is very important. That's called order parameter. Okay, so there is something called order parameter. So what is an order parameter? So you have typically a order disorder phase transition. Order disorder. This is the phase transition. You have an order disorder phase transition. Now your order parameter is such that so order parameter is defined. Okay, so this is defined such that such that its thermal average. Essentially, thermal average is an ensemble average, what we are familiar in statistical mechanics. This thermal average is zero in disordered phase. Zero in disordered phase and non-zero in the ordered phase. Zero in the disordered phase and non-zero in the ordered phase. Okay, so there is no general rule or a general idea as to how to define an order parameter, but one has to do some kind of a physical intuition plays some role here. So in general, given a second order phase transition, we should be able to define an order parameter. So for example, in magnetic system, okay, so magnetization. Okay, so we call it as M. Magnetization is the order parameter in paramagnetic to ferromagnetic transition. Right? In paramagnetic phase, your magnetization is zero. Ferromagnetic case, magnetization is not zero. Okay, so the magnetization is essentially it is related to some of the spins, right? So this is what is called the order parameter. Now what we are trying to calculate is, so this correlation function is going to, so this correlation function as we defined here is actually going to tell us the fluctuations in the order parameter. Okay. As you can see here that our S0 is the order parameter here, because I have, this is like magnetization. So this is the order parameter, and this is so this one will actually captures fluctuations in order parameter. Okay, and this are the correlations in the order parameter. We actually derived. Okay, you can it can be derived from quantum field theory, because essentially these interactions are treated using quantum mechanics, because the dipoles, the origin of dipole is also can be uh, treated quantum mechanically, quantum field theory. So you can use quantum field theory and you can show that this kind of a behavior is, that is something which can be derived. Of course, you can see from experiments this is what is kind of a behavior. But note one thing, that this is essentially true only if T is not equal to Tc. Okay, at all temperatures other than Tc, your correlation function will have a behavior like this. It is an exponential behavior like this. And you can always estimate this xi by fitting the experimental data from the scattering experiments. And then you can obtain what is the answer. And interestingly, at critical point, what happens at T is equal to Tc? There is a significant change in the system, and the 2-point correlation function takes instead of power law behavior. So you can see this is an exponential behavior, but at T equal to Tc, your 2-point correlation function takes a power law behavior. Because this D here is the dimension of the space. That is, we are talking about 2-dimension or 3-dimension. Okay, so dimension of the space. Okay. And this is uh, eta is an exponent here, and this is in some sense our first encounter to what is called a critical exponent. So it will have a behavior like this. This correlation function will have a behavior like this. Now let me say that one of the important and very exciting aspects of this second order phase transition is that it's not this exponent alone, but there are a host of other exponents, okay, which are given in this table. For example, let's say you have a magnetization. Okay, so look at this exponent. This is called, in general, this is called order parameter exponent. Order parameter exponent. So in this example of magnetic phase transition, our order parameter is magnetization. So magnetization will be 0 in the disordered phase for t less than Tc. Okay, even if the limit b equal to 0, the magnetization will change as Tc minus t to the power minus beta. That means your magnetization will be something like uh, 1 over Tc minus t to the power power beta. Okay, it
Sir?
also diverges, and then this eta is this exponent. So you can see alpha,
Sir,
beta, gamma,
sir,
delta. Yeah.
the presentation is not visible, sir.
Is it visible?
Yes, sir, now it's visible.
I do not know why it's going off. A minute. Okay. So alpha, beta, gamma, delta, nu, eta. So as far as this critical, I mean the second order phase transition of some systems are concerned, so these are the exponents, and so there are so these exponents. It turns out that they are they can be experimentally obtained, and it has been an experimental fact that uh, you can establish the values of these exponents from the experiments. Now, when people try to look at these values, and then they realize that these values uh, has some kind of a mystery, in the sense that the numerical values that you are getting for these exponents, they turn out to be same. Okay. For example, all these exponents are same for liquid to gas phase transition at critical point, and they are also same for paramagnetic to ferromagnetic phase transition, and they are also same for superfluid to normal fluid transition. Even though the microscopic constituents in each of this case, for example, in the case of solid liquid to gas transition, the microscopic constituents are atoms or molecules, and the interactions between them are like typically van der Waals like interactions. In the case of paramagnetic to ferromagnetic transition, the microscopic constituents are magnetic dipoles, and the interaction between them is dipole-dipole interaction or a spin-spin interaction. And in the case of superfluid to uh, a normal liquid transition, there is a strong overlap of the wave function, and of course there are other interactions. So you can see that in different uh, types of phase transitions that are giving rise to same set of critical exponents, numerically the values, their microscopic constituents are different, the nature of interactions are different, and yet they give rise to same set of critical exponents. So this was very surprising and intriguing, and it turns out that of course people try to look at several examples and then categorize a host of systems that have the same critical exponents, and they have come up with this notion of what is called a universality class. Okay, Okay, so that is what was the genesis of a universality class. Okay, so we have this idea of universality class. Okay, so what is this universality class? That uh, so systems exhibiting phase transitions, phase transitions with the same values of critical exponents. Same values of critical exponents are said to be in a universality class. Okay, and this is one thing. The other thing is that they observed what is called uh, some kind of a scaling behavior. That means, uh, for example, if you take if you take yeah, so scaling behavior, this gave rise to kind of a relations among critical exponents. That means not all critical exponents are independent, but they are related. Okay, so critical exponents are related. Okay, that means basically if you say that, okay, I am trying to um, dilate the system, that means if I make lattice parameter as some lambda times lattice parameter, then I will be appropriately, I will be able to scale my order parameter such that the correlation length will acquire a different exponent. So it will be possible to now connect all these critical exponents. So that kind of a scaling behavior is observed. And then universality class has been universality classes have been classified. Now, understanding these things, that both the scaling behavior and universality class uh, has kind of was completely understood only when people developed what is called a renormalization group in 1985 by A.G. Wilson, who was able to explain that uh, your system, see, basically it is something like this, that since there are correlations which are diverging, that means the entire system is like one single entity. So the scale, the length scale over which you are looking at the system is not important, because, and also remember that when we started our interactions, we said we are having only nearest neighbor interactions. So you have a short range interaction, but this short range interaction is leading to kind of a long range correlations at the critical point, and hence the smaller time scales are not important. So what renormalization group analysis does is that it provides a scheme where you can actually go from smaller scales to progressively higher and higher scales by appropriately scaling your Hamiltonian, and you define a kind of iterative map such that this kind of a scaling can be systematically carried out, and then this scaling will have some kind of a what is called an equilibrium point, or a point which is called a fixed point, and that fixed point Hamiltonian, or that fixed point physical system will is supposed to have a behavior, and that behavior is what gives rise to these critical exponents. So this is in some sense the qualitatively how renormalization uh, group can be understood. So this is one line in along which one can explain this, but we are not really going to do that because that is a very big project in itself. And if ever you uh, happen to take your advanced course in statistical mechanics in any of your PhD later, so you will definitely study this. Uh, uh, so let's try to see what best can be done within uh, our whatever we have understood. So you can see that. So one important thing is that to make any progress with the phase transitions, let's say that our aim is to let's say we have. So can we get critical exponents? Can we get critical exponents um, estimated from theory? Estimated from theory. First, we have been able to get them from the experiments. Okay. So if we ask this question, then we have to deal with we have to deal with an interacting system. Because as I told you that interactions are important, interacting system. And interaction systems don't have so there are no general methods to exactly solve. So one of the important thing is exact solutions. Exact solution is hard and not possible in many cases. And how do we make progress? We can make progress in two different ways. Okay, so two ways to make progress. And the first way is approximate approximate interactions. And this particular method goes by the name called mean field theories. Okay, so if you approximate your interactions in mean field theory, you can solve that exactly. Okay, but then you don't know you're not treating the same interaction, but you're getting only some kind of a what is called an approximate result. Okay, so then you can try to um, in field theory, and then add corrections perturbatively. Add corrections perturbatively. So this is one approach, and largely this approach is very important because many people try this approach. The second approach is um, computer simulations. So here you don't approximate interactions. Okay, so in computer simulations, interactions are treated exactly. Interactions are treated exactly, but uh, a finite system is simulated, because you cannot say that I will do a thermodynamic. I'm simulating a system in thermodynamic limit. A finite system is simulated because computer memory is limited, time is limited, so you can only do a finite system. Okay, and then to get thermodynamic result, to get thermodynamic result, we have to do what is called a finite size scaling. A finite size scaling. We have to do a finite size scaling. So in these two alternate ways, one can make progress. And again, since we don't have our course is not meant for doing computer simulations, I will not proceed doing this one. But let's try to do some simpler analysis of how to do this in field. Okay, so yeah, so let me now uh, concentrate on asking uh, questions like this. How do we choose order parameter? As I told you earlier, that uh, we don't have any kind of a rule or a procedure by which you can choose this one. But one guideline, or in some sense, one guideline that we have is or a thumb rule is that uh, your order parameter and share the same symmetry. Okay. This is not sufficient to identify unambiguously, but it should share the same symmetry. Now, why this is important? Um, this is important because let us try to understand this. This is an important concept. So let's try to understand why this is important. See, for example, if you take this Hamiltonian of a magnetic system that we have talked about, the Hamiltonian is something like minus j over 2 sum over ij si dot sj. This is what I have written earlier also, si dot sj. Now, if this si is is a vector in 3 dimension. Okay, so Si is a vector in 3 dimension, and Si dot Hj is a dot product of two vectors, and the dot product is invariant under rotations in 3 dimensional space. Okay, so we can say that the uh, this H, the Hamiltonian, is invariant variant under under rotations in three dimensions. Okay, and I'm sure you learned a little bit of group theory language in last semester. So if this is invariant under rotations in 3D, then we can say that this is invariant under these rotations in 3D are they all form something called SO3 group. Even if you don't know what it is, it doesn't matter. Essentially, all types of rotation matrices uh, about a point in three-dimensional space will, if you put all elements together, it's an infinite continuous group, and that will form this SO3. And like in classical mechanics, what you studied, these Euler angles will be like parameters of this group, and those matrices that you wrote down with Euler angles will become kind of a generators of this group. So this, okay, so let's not too much give importance to this group theory language. But what I'm trying to say is that you make any rotation, the Hamiltonian does not change. That is the symmetry of the Hamiltonian.
Sir,
Yes. Yeah.
so what is the difference between a special orthogonal group and a dihedral group, sir?
Um, that's what I said. I do not want to go into the details of this group theory.
Okay, sir.
Dihedral group is a discrete group. Okay, with so it can be defined with any rotation axis, whereas SO3 is a continuous group of all possible rotations in 3 dimensions.
Okay, sir. Thank you, sir.
Okay, so now what I want to emphasize here is that when you define your order parameter, as in the magnetic situation, our order parameter is the magnetization. When you define this magnetization, now in high temperature, that is paramagnetic phase, magnetization is zero. Okay, so magnetization is zero. That means this is also invariant. Is also invariant because there is no specific direction associated with the magnetization. So this is also invariant under SO3. Okay. So your order parameter is also invariant under SO3. Now, interestingly, what happens is that uh, for for t less than Tc, this magnetization will be a particular direction. As I have said, it will be a particular direction. Some particular direction is fixed, right? So that means uh, so for t less than Tc, H, the Hamiltonian is invariant because Hamiltonian is same. Hamiltonian is invariant under SO3, but the order parameter, the magnetization, okay, is not invariant because there is a specific direction now, not invariant under SO3. But instead, it is invariant under only rotations about this axis, not invariant SO3, but only invariant under rotations, the rotations of about the direction SO. That means these are rotations on the plane. Okay, rotations on the plane. So that means what? This implies M is invariant under a smaller subgroup that is called SO2. So, what actually is happening is that at high temperature, that means in the disordered phase, both H and M are invariant under. Okay, so this is an important concept. So that's why I'm trying to spend a little time. At high temperature, both the Hamiltonian and M are invariant under SO3. Now you decrease the temperature. When you go to low temperature, okay, so low temperature, H is invariant under SO3, but M is invariant under only SO2. Okay, and this SO2 is a subgroup of SO3. Okay, so this is something which is a kind of a characteristic feature of this kind of a phase transitions. This is called symmetry breaking. Okay, so this idea is very profound in the sense it is the same idea which took shape in the same idea is what is used in Higgs mechanism, for example. In Higgs boson, the Higgs mechanism, which is very important for giving mass to the gauge bosons in electroweak theory, there also you have a Lagrangian with some particular symmetry, and the solution of the field of the Lagrange's equation also sharing the same symmetry. But at some particular point, the solution or the field does not obey the symmetry same as what Lagrangian obeys. Exactly like your Hamiltonian order parameter share the same symmetry, and at low temperature, Hamiltonian shares a higher symmetry, whereas the magnetization shares a lower symmetry. The same way in Higgs mechanism, your Lagrangian and the field they obey same symmetry, but at some instant you will see that the field does not field actually shares a lower symmetry, and hence uh, that kind of a symmetry breaking is what leads to Higgs field and Higgs boson and so on. So this idea is borrowed from this field, and this particular so any such symmetry breaking transition or symmetry breaking thing. So in order to capture this one, at least it is important that we should have the order parameter and should have the same symmetry when we actually construe the idea of what an order parameter is. Okay, so this is what is the importance of symmetry breaking in. Uh, so in the same way, you can see that. So you So it is important to understand what kind of group of operations leave the Hamiltonian invariant whenever you are trying to look at any phase transition. So this is one of the uh, ideas that has a very important role. Okay, so next we will try to ask question that having understood to some extent about the order parameter, we can see that if you have, for example, if you take a thing like a magnetic phase transition. Now, magnetic phase transition, we are trying to build our understanding from the magnetic phase transition. So, let's say that I want to talk about an ordered phase. So, that means I have all the spins aligning in one particular direction, let's say up direction. But then energetically, I will not be able to distinguish instead of all the spins aligned in the up direction are all aligned in the down direction, because this up and down are something which are actually meaningless energetically, because all of them are in the same direction is what is important. Now this tells me that this kind of a what is called a parity symmetry tells me that I have a magnetization m or a magnetization minus m. The energy should not change, because it doesn't matter whether it is aligned in the up direction or down direction. So that tells me that my free energy, okay, so my m, okay, so m um, or minus m doesn't matter. That means I have all possible spins aligned in this direction, or all possible spins aligned in this direction. That should be same. It depends on whether I apply magnetic field in this direction or I apply magnetic field in this direction. Okay, so this should be completely symmetric. Now this tells you that you have some kind of a dependence on the order parameter to the what is called the free energy. Okay, so this understanding has led to development of a theory due to Landau. So let me just tell you this Landau mean field theory. Okay, so this is called Landau. Or it is sometimes called Landau theory of phase transition. So, um, so let us now define two things. Let me say I will define m as my order parameter. Of course, I keep the back of my mind. There is a magnetization. M is supposed to be magnetization, and then I define my T as T minus Tc minus T over Tc. Sometimes it is called reduced temperature or scaled temperature, whatever. So I'm going to assume that uh, so Landau tried to say that let's high be the free energy. So for second order second order phase transition, Landau assumed that the free energy admits an expansion in order parameter. M. That means your psi of M can be written as um, some kind of a Q plus. So you can say this Q will be a function of T. Then there is an R of T M square plus some S of T M to the power 4 plus etc. So this kind of an expansion is what Landau assumed. Why this kind of an expansion? Because psi does not contain odd powers of M, because psi of minus M should be equal to psi of M. If odd powers of M are, that is this symmetry that I am talking about. All of them up, all of them down, the energy should not be same. So this is the requirement, and because of this requirement, the odd powers will not be there. Okay. Now further, you can argue that this Q of t, R of t, S of t, these are functions of, these are coefficient, these are functions of this. So let's say maybe I can say that my Q of t can be written as sum over some j is equal to 0 to infinity and q0 or qj into t to the power j. Okay, and of course my r of t can be written as sum over j is equal to 0 to infinity rj into t to the power j. Okay, these are some kind of a well-behaved analytic kind of a functions like this of temperature. So they can all be expanded in terms of the powers of this Sj. Of course, note that we will be interested in so the interest is very close to Tc. Okay, so um, so the interest here is uh, small. That means T close to. That's our interest. Okay, so that means we, even though this depends on these powers, but since T is small, we can actually neglect higher order terms and then look at certain initial. Now, what is our so the equilibrium or the equilibrium property will definitely corresponds to minimum of the free energy. Okay, so let us try to minimize. Okay, so minimize psi with respect to m. Okay, so if you try to minimize that, then you will have, of course, you have to take the psi by the m equal to 0. That gives us r of t m plus 4s of t m cube is equal to 0. Now this gives us three solutions, the cubic equation. One solution is m is equal to 0. So that is given by, I have m here and m cube here. So m equal to 0 is one solution. The other two solutions are m is equal to um, plus minus square root of r of minus r of t divided by 2s. Okay. So there are three solutions: m is equal to 0 and r of t to 2s. So let us try to understand this one carefully. So let's say that so let us assume this. Assume that r 0 is 0 and r1 is greater than 0 and s0 is greater than 0, and neglect and rj is 0 for all j greater than 1 and sj is 0 for all j greater than 0. Suppose let's assume that. So this is what, under these conditions we have m is equal to 0, that is one root, and then the other one is m is equal to plus minus square root of um, minus r1 into t divided by 2 times s. Um, I think I have to define this t in the following. I define t as t minus tc divided by tc. So please make this change. The way we are doing this thing, I'm going to define just t minus tc divided by tc. Okay, you will understand why this is important here. Now, what happens is that let's say you consider high temperature region. This high T. That means we have T greater than Tc. Now T greater than Tc, this implies that your T is greater than 0. As T minus Tc is greater than 0. T is greater than 0. In that case, what happens? Since R1 is greater than 0, T is greater than 0, and S naught is greater than 0. Okay, our M is equal to plus minus root minus R1 T divided by 2 S naught is imaginary, not a real roots. Basically, these are complex, imaginary roots. Okay, so that means this implies essentially M is equal to 0 is the only real root. M is equal to 0 is the only real root. Now let us look at dou square psi by dou m square. Dou square psi by dou m square is 2r of t plus 12 s of t m square. And suppose you want to evaluate this dou square psi by dou m square at m is equal to 0, that is at that root, then it will be simply 2r of t. And we have second this r1 to be r, which is greater than 0. That means psi is minimum at m is equal to 0. Psi is minimum at m is equal to 0 in this region. That means we are talking about high temperature. Okay. So if you care to plot this one, that means if you say that this is your m and this is your m is equal to 0, then your psi is something like this. it is has a minimum at psi is equal to 0. So this will be your psi of m, and the value of that one is simply given by that q of plus r and s terms have m equal to 0 is substitute, then you get only whatever this q is. Now what happens at low temperature? That means for T less than Tc, T less than Tc, then T becomes negative. Now because T becomes negative, this is a real root. T becomes negative. So m is equal to plus minus R1T by 2S naught are real roots. Now because they are real roots, we have three solutions. So we have three real roots. M is equal to 0 and m is equal to plus minus, call it as some ms. Okay. Where ms is equal to this particular value. Now let's ask what is so this is basically 2r1 into t. Okay. Now what happens when you look at dou square psi by dou m square at m is equal to 0, that's equal to 2r1 into t, but since t is less than 0, this is less than 0. This means psi is maximum at this point. Psi is maximum at m is equal to 0. What was the minimum in the previous case has now become maximum at m is equal to 0. Now what happens to this one? Then let's say I talk about dou square psi by dou m square at m is equal to square root of minus r1t by r1t divided by 2s naught. Okay, or plus minus whatever. Plus minus it doesn't matter because we have only square here. That is 2r1t plus 12s naught into minus r1t divided by 2s naught. Okay, so this s naught will cancel, and you have 2r1t 6, that's equal to that's equal to 2r1t 6 r1t, which is equal to minus 4 r1t, but t is less than 0 and hence this is greater than 0. So we have psi is minimum at m is equal to plus minus square root of minus r1t divided by. So you can see that this means that your so you look at this expression. We have a situation like this. Suppose you have your free energy is something like this at the temperature. This corresponds to t greater than 0, and when it becomes less than 0, then you will see that you have. So let's say that for some other temperature which is smaller, perhaps than this one is also for t greater than 0. Now when it comes to t less than 0, then you have a minimum and a maximum here, and then again a minimum and then a maximum. This is for t less than 0. Okay, so what I'm plotting is m versus psi of m. So the nature of this free energy changes at t equal to 0. That is at t equal to capital T equal to Tc, and this is what leads to phase transition. So this is like so this particular minimum corresponds to, let's say, all spins, down
Sir?
hello.
Yes, sir.
Yeah. So when did I leave the meeting? Have you heard of this other parameter exponent? Do you see the screen?
Yes, sir.
So up to what was when I left, I was talking about this
Sir, you are just talking about
m
these two minimums.
two minimums. Okay. These two minimums actually characterize. So this minimum is something where we have this is the negative, right? So this is m is equal to minus ms, and this is m is equal to plus ms. That means this corresponds to all spins up, and this corresponds to all spins down. Now, with respect to critical exponent, as we have seen that this m is like this, so if I want to write it in this fashion, from this theory we get this beta to be half. So this exponent is half, but experiments show that this exponent to be something like 0.33. So what we are getting from the mean field theory is not same as what is experiment giving. So that is where this perturbative corrections are important. So mean field theory is not exact. It will not give you the exact critical exponents, but nevertheless it will give you some idea of what what kind of things are required to get these critical exponents. Okay, so this is one exponent. So we can also talk about. So now let's say that suppose if I have for getting the other exponents, I want to show that let me just draw your attention to this list of exponents that we have shown in the beginning. Let's say, yeah, so these exponents. So whatever I have shown just now, this beta is like half. That's what I have shown from mean field theory. So mean field theory. Mean field theory is now we can ask what is this gamma and what is this delta and so on. So some of them I will show you from this mean field theory how to calculate. Uh, in principle, you can calculate all other things also. Let me just show you. So now let's say that we will uh, we will apply magnetic field. So far we did not talk about magnetic. So if so in the presence of field, the presence of field, let's call that as some h. Okay, so we have our free energy will have a form like this. Your psi of m will be equal to. So you have an additional term h into m. Okay, this will be minus h into m. Okay, this plus you will have your q of t plus r of t m square plus s of t or 4 and so on. Obviously, when you apply field, there is no symmetry of both m and minus m because that direction will be picked up. So that means symmetry breaking takes place because of the applied field. So this is the free energy that you will have if you have this one. Now suppose if you minimize, okay, so now you ask what is your dou psi by dou m equal to 0. This implies this you get minus h plus 2 times m r of 2 times r of t into m plus 4 times s of t m cube. And of course, there are higher order terms which we are anyway going to neglect. Okay, so now you can ask a question that so we have so this should be equal to 0, correct? So that means I will have h is equal to I can take h on the other side. So 2 r of t m plus 4 s of t to m cube. 2 r of t into m plus 4 s of t into m cube. Now you can ask a question that you have uh, so that so you can first ask what is your chi. Your chi is dou h dou m, that is the minus one. That is basically magnetization. The derivative of magnetization, the magnetic field is your chi. So since I have this expression, so I can write it like this. So what is your dou h dou m? H dou m is 2 times r of t plus 12 times s of t m square. So this chi is basically 1 over 2 times r of t plus 12 times s of t m square. Now I, as usual, take r of t to be r1 into t and s of t to be simply s naught. Okay, so if I use this, okay, so use this like in the previous case, then I will have this chi to be equal to 1 over 2 r1 t plus 12 s naught into m square. So now I want to substitute this m square because the other parameter is known at the TC. So if I ask what is that, so for the roots that we know that this m square is minus r1t divided by 2s. Okay. So if I substitute that, I get chi is equal to 1 divided by 2 r1t plus 12 s naught into minus r1t divided by 2s. So that is what will give me the sky to be equal to 1 by 2 r1t minus. So you can see s naught will cancel minus 6 r1, so which is equal to 1 by minus 4 r1. Okay, so if t is negative, then this will be like 1. This minus sign doesn't matter, but you can see that this tells you that your chi will go like e to the power minus 1. Okay, so that means our susceptibility exponent, as you can see, defined in this fashion. So the susceptibility exponent, this gamma, it turns out to be minus 1 according to our mean field theory calculation. Uh, yeah, so that is one thing, and then we have from here. So we have now at if you look at this at t equal to tc, at t equal to tc, you can look at this exponent, for example, at t equal to tc. That means this corresponds to small t becoming 0. Okay, so you look at this expression, and this expression is the dependence of field on this. So use these things, then we have h is equal to 2 times r1 t into m plus 4 times s naught into m cube. Okay. Now h at t equal to 0 is equal to, this term will go to 0, and I have 4 s naught into m cube. Okay. In other words, if you look at this exponent, how is it defined? look at this exponent. B is proportional to m to the power delta. So that means we have shown this delta to be equal to 3. That is proportional to m cube. Okay, you can actually also talk about other exponents, but this is how, using a mean field theory, you can get critical exponents. But as I told you, that these critical exponents are not same as the exponents that we get experimentally. Exponents that we get experimentally are somewhat different, and we have. Let me just see if I can show you some list of exponents. Are experimentally in it. I will. So I'm just trying to. Yeah. So I don't know if you can see this. This is a set of critical exponents. Can you see this table?
Yes, sir.
So this beta is the critical exponent for the order parameter, which our mean field theory shows it is 0.5, whereas experiments in magnetic systems is 0.3 to 0.6. Gas-leak alloys, ferroelectric system, superfluid, of course, did not measure. Our measurement is not available. So this table I'm choosing from this Patria. I've shown this from Patria, and I think yesterday I wrote a different name. The other name is Real. I think I was writing a name, second name, which was the second author of probably Goldstein book. So and this gamma and gamma prime exponential, but on both sides. Okay, so they are showing two different sense. Similarly, alpha and alpha prime, our mean field theory shows it is one, as we have already shown, whereas the experiments show them to be slightly larger. Whereas this delta, the field exponent that we have shown that it is 3, but experimentally it shows a bigger value than. Similarly, this nu and eta are the other exponents which we did not derive. But so there are two things that I want you to notice here is that even though these phase transitions are different physical systems, but their exponents are same. That means these all come under what are called same universality class. But then we can get some exponents uh, estimated from the mean field theory, which are not going to coincide with what is observed, but they give some indication. Now you have to do what is called a progressive perturbative corrections, so that your theory also will give exponents which are close to the experiment. So that will be the next step. But I'm just trying to show you the simplest first step of doing a mean field theory using this Landau theory. Okay, so I will stop here. If you have some questions, we can discuss. I didn't talk about Ising model today, but maybe in the next class, I will start with Ising model and then see how, by a systematic analysis of some approximations, we can get the same exponents from the Ising.